Thank you. Okay, for those of you who don't know about ffA, we started off, as Dave said, in the mid-1980s as a medical imaging company. So our expertise was on analyzing images from the medical world, primarily microscopy images, but also CT images. And so that gave us a different way of looking at images and a different way of analyzing changes and variations within images. And then about 15 years ago, we were approached by Shell to see if we could adapt our technology to work on seismic data. And so for the last 15 years, our focus has been adapting existing image processing techniques, but also developing new and innovative ways of using image processing to look and analyze seismic data, particularly 3D seismic data. So we've got a very strong background in medical imaging. My personal background is actually in neurophysiology. So I studied transmission in the brain for several years. So I look at things in a slightly different way. When I look at seismic, I look at it as a 3D image, and I look at it as the changes that we have in the image rather than thinking of it in conventional geophysics terms. So what does that mean in terms of seismic data and interpretation? How can we help? What does it that we bring to the industry? Well, if we think about whether we're working in frontier exploration, where currently certainly you're working in very inhospitable environments, possibly deep water, the exploration costs are very high. You've got a lot of uncertainty there. And likewise, when you're working in mature basins, looking at extending the life of fields that are already in production, you've got a lot of marginal returns. You're looking at very subtle geological differences to extend the life of your reservoir. So in both situations, you're making decisions that affect the economic success of your reservoir based on your understanding of the subsurface and your understanding of the geology of the subsurface. And it's fairly easy to see that better information of the subsurface is going to lead to an improved understanding of the uncertainties in your interpretation. And that will then lead to more informed decisions and hopefully, therefore, better economic success. And when it comes to better information, seismic data really is our best source of subsurface information. It's the only way we can get the lateral resolution that we need to understand what's happening under the earth away from our well data. And the industry knows this, which is why it spent $8 billion approximately last year on seismic acquisition and processing. It really is the key to being able to understand what's going on under the subsurface. So most of the 11.5 million square kilometers of licensed offshore acreage is now covered by seismic data, be it 2D or 3D. And pretty much the same can be said for onshore data as well. So seismic data is key. And we've seen already today some of the improvements that you can get with new seismic processing and acquisition techniques. And they are going to be really helpful in helping us understand the subsurface. But the data itself actually has no worth. The value of the data is in the information that it contains. And that is fundamental, because there's no point having lots of data if it's sitting on your shelf. You've got to be able to get the information out of it. Conventional horizon and fault interpretation techniques only capture a small fraction of the information in the seismic data. You know, the broadband seismic that we saw earlier from PGS giving us so much more information, but if we're only interpreting every 10th line, you're throwing half of it away. You're not using it. So you need to be able to access all the information that's in the seismic data. And the only way to do that is to analyze the seismic character on a point-by-point basis, to look at every line, every cross line, every voxel. And that's what attribute analysis is doing. And attribute analysis is definitely a growing area in the industry. A lot more people are using it, and it's becoming a very valuable tool. But doing more processing, and arguably attribute analysis is another form of processing. So doing more processing can lead to information overload rather than better understanding. You can just have so much data and so much information, but you need to be able to understand that information, because the value of information is in the understanding that it confers. So you've got to go from your data through the information to get the understanding coming through. And that's really where we've been working, and what we're looking at is we're trying to develop new ways of helping the understanding of the interpreter increase. And we're doing that with a new type of interpretation paradigm, a new way of working, which we're calling geological expression. And what geological expression is a data-driven but interpreter-guided method for highlighting and extracting the geological features in your data. So it's not just about processing, and it's not just about interpretation. It's about the two aspects working together, hand in hand, so that the understanding of the subsurface increases and we can all make better decisions because of it. So what do I really mean by this? You know, what does this actually do? So if we start off with the reflectivity data, so this is a cube of seismic reflection data, and there are a lot of interpreters who are still using this as probably their only form of data on which to base their interpretation. So we've got a channel and a fan system in there. Now it's actually really hard to see. You might get a bit of the channel up here, but that's about it. So to actually interpret that is going to take a lot of time because you can't really see it. So the first stage in a geological expression workflow is to do the attribute analysis, to analyze the subtle character changes in your data so that you can actually start to see the geology. And what we have here is an RGB blend of 3 frequency response volumes, and we can start to see the channel coming down, and you can see it fanning out down here. Now, we can see this because the human eye is very good at identifying shapes and seeing objects that we recognize. So as interpreters, we recognize a channel and fan system. Those are geometries that are familiar to us. And so we can start to see that in here. But when you actually look at the color variation, you know, you've got browns up here, blues, greens, browns, reds, whites, and oranges down here. So it's still a very complex image. And at the moment, there's no way of extracting that in a data-driven manner because the character of that is so variable. All our geobody extraction techniques at the moment are threshold-based. So you can't define a threshold that incorporates all those values, but doesn't incorporate all that as well, okay? So that's what the next stage of the geological expression workflow is the development of new innovative techniques that allow you to extract out those geological features as 3D geobodies, to do your interpretation in a data-driven way, but still have interpreter guidance in there as well, so that you, as the interpreter, can put your knowledge into it, but you can let the data speak as well. So these two geobodies that we have here were tracked on this RGB blend. So we've got this new technique that allows us to extract out geological objects that have a changeable characteristic within them. And we can do that because we're using the interpreter's knowledge to help guide the process at the same time. So the geological expression workflow is the complete interpretation workflow in terms of identifying the geology in your data. You start off with your reflectivity data, and you start off with data conditioning to improve the signal-to-noise ratio, to minimize any residual noise that might be in there. And then you go through the standard stages of data reconnaissance, so lead identification, prospect generation if you're in an exploration environment. You can go in to do some complex fault imaging, so identify your structural settings. Then go on and do your standard horizon interpretation, your geobody delineation, and also fault interpretation and analysis. So starting to pull out these geological features and build up your interpretation, and then finally ending up with your FACES classification, which can then lead into your geological modeling and your well planning. The fundamental difference with the geological expression workflow is that this is all based on a data-driven paradigm. So the data undermines and underpins, rather, everything that is being done here. It is the core of the interpretation, but it's still being guided by the interpreter. So it's that combination of data and interpretation simultaneously, interactively. If, as is often the case and has been done for the last 25 years primarily, we've been doing manual interpretation. Okay, this is where you as an interpreter sit down and we manually pick our horizons, or we manually pick our channel tops and our channel bases. And by doing this manual interpretation, we can bring in a lot of information that actually isn't in the data. So the geological context, the analog information, our experience knowing the behavior of channels, knowing the behavior of carbonate systems, how reefs build up. We can bring all that kind of peripheral knowledge into our interpretation. And that kind of knowledge is essential. You know, we need to incorporate that into the interpretation. If we do things on a purely data-driven approach, we get very high resolution results because we are interpreting every line and every trace. Whereas with the manual interpretation, you're probably only interpreting every 10th line. So the data-driven approach, you get that high resolution and you get the very objective analysis as well. And it's very rapid, so you can get results very quickly and very objectively. However, they can also be wrong because the data is at best an ambiguous representation of what's going on in the subsurface. It's the best one that we've got, but it isn't perfect. There are often multiple interpretation scenarios. You know, there are often choices to be made. And a purely data-driven approach can't really make those choices. It will tell you what the strongest likelihood is according to the data, but it can't bring in the geological context. It can't bring in the analogues. And it also doesn't help the interpreter's understanding. You know, if you do a purely data-driven interpretation, you'll get lots of volumes out, but you won't actually know what they mean unless you've gone in and looked through them and worked with them. So you don't actually gain much by doing a data-driven approach on its own. It's only by having the two systems working side by side and in balance that you get the most understanding about the subsurface. You can bring in your geological context, but you can have your objective data-driven analysis at the same time. And that's what geological expression is. It's this balance between manual interpretation and the data-driven interpretation. So to be successful, a geological expression workflow must also give you on-demand extraction of geological features. Because when you're interpreting, you're thinking about things, you're trying things out, you're looking to see where things go. You don't want to wait for 2 hours while your computer processes something to then come back, because then you've gone off and you've thought about something else. So whether it's fault delineation, so automated fault delineation, which is a lot more accurate and reliable than we currently have, or whether it's geobody delineation, which is robust to variations in the character of your features, because you know, inevitably, especially your channel systems, are not going to have a consistent character all the way down. Or whether it's seismic facies classification, where you want to do a full classification, but you also need to incorporate your well data into that as well to guide it. So all of these things need to be done interactively and at the same time as you're interpreting and at the same speed that you're interpreting. So the speed of analysis has to equal the speed of interpretation for the geological expression workflow to work. And that has been nigh on impossible until now. When I first joined ffA 11 years ago, it would take us a week to create dip and azimuth volumes on a 200 square kilometre data set. It was painful. But things have sped up a lot since then. Computing technology has come on a long way since then. So the first big step was with the introduction of dual core and quad core CPU systems, because that meant things sped up really quickly and we got significant improvements in processing ability. And then in the last couple of years, we've had another big jump. And this is because of the advances that have been made in the gaming industry and what they've done with graphics cards. So we can now use the power of the graphics cards to help our computational speeds. So we can use the GPU, the graphics processing unit, in collaboration and conjunction with the CPU to get much, much faster processing speeds. And this means that we've now got, we can now do interactive processing. This comes at a cost though. It's much harder to write software that works on a GPU than works on a CPU. And there are also a lot of different graphics cards out there. And there are a lot of different GPU and CPU configurations that are possible. And they're not static. You know, computer technology is evolving all the time, very, very quickly. So these will continue to evolve and continue to change. So the software has to keep up with that. We need the software to be able to adapt and to make the most of these changes in the graphics cards, as well as changes in the CPU technology. So that in itself gives us a developmental challenge when it comes to actually writing the software. But that is a challenge that we have to overcome to be able to deliver software that can be interactive and that you can work with at the speed that you need to. But why do we really need this speed? Does it have to be this interactive? Well, when you're interpreting and you've got different scenarios, you need to be able to investigate the different scenarios. And if your computer can't keep up with you, then you're not going to be able to investigate them properly. You're not going to be able to use a properly data-driven approach to help guide your interpretation. So the analysis has to be able to keep up with your train of thought so that it can help guide the process and be an effective tool, not just something that's done on the side if you have time. It's got to be able to be incorporated. But we've also got to minimize the data overload because there's a lot of data already and we're getting more data all the time. So we don't want to be generating reams of attribute volumes that we don't actually need or don't actually use or don't actually look at some of the time. So we need to be able to identify which ones are relevant, which ones are important, and which ones are needed, and incorporate those in really quickly. So an interactive approach allows you to do that. You can see what you're looking for, you can see whether it's there or not, and if it's not, you don't process it. And if it is, then you take it further, and you can use it and integrate it. But it's more than just number crunching. Software design has to be more intelligent than just the ability to run algorithms. It's got to cope with the large geological variations that are in the data. So, it's got to be able to look for your subtle stratigraphic traps, but also identify your salt domes, two very different extremes of geological features with their very different data characteristics. And I'll come on later into how we're tackling that. It's also got to provide new information. There's no point doing things if we're not actually getting more information and therefore more knowledge. And we must also recognize that seismic doesn't give us the whole answer. We need that trio of knowledge, experience, and information to build our understanding. And we mustn't exacerbate the problem of data overload or mustn't forget about the flow of information, because software companies like us, who are small, have to integrate with the bigger companies where sort of have the interpretation packages that are on all your desktops, because those are the ones that you use every day. So we need to be able to integrate our technology or the results of our technology into yours so that you can get the full value of it. So I'll look at some of these first 3 points in a bit more detail. But to create this and to be able to deliver this requires a new paradigm of software design, a new type of geophysical interpretation software package. And that's what Geoteric is. So Geoteric is a geological expression software which directly translates your geophysical data into geological information. And it does this in a data-driven but interpreter-guided approach, so that at all stages, you as the interpreter are building your knowledge as the data is being processed. This type of application doesn't exist in the market at the moment. This is the first example of this type of methodology of working. And it's a methodology that has interactivity at the very core of it. and it's also intuitive to use. So it can become the very heart of the interpretation workflow. One of the things that's core to the geological expression workflow is the geology directed workflows. There are many different ways to analyze the seismic data, but to really identify the geology that you're looking for, it helps if you can be directed as a user through the workflows that are most effective. So having geology directed workflows to guide you through the process and get out what you want. And we can drill down into this into a bit more detail. Say, for example, if we're looking at clastics, we can look specifically for injected sands, sheet sands, stratigraphic traps or channels, using the workflows that are most appropriate for that, guiding the user all the way. We also use color visualization a lot because this is very effective at combining multiple volumes together. So here we've got 3 attribute volumes. One of the problems with sort of fault imaging is that one fault attribute rarely actually gives you the full picture of your faults. You often see just part of your faults. And that's because the expression of your faults changes along the fault and down the fault. By combining different attributes together, we can detect those different seismic character changes, and we can see that in the different color of the faults in the image here. Now, those different colors relate directly to the geology because they're picking up the different expressions. So what we can see here is that these turquoise faults are going through more ductile rocks. The red faults have a bigger displacement and potentially a change in lithology or fluid fill across the fault. So you can start to get geological information from your geophysical data by using these workflows. This is another RGB blend of a frequency decomposition, 3 frequency decomposition volumes. And I think this really kind of epitomizes a geological expression workflow because this image was taken from seismic data. It's offshore West Africa, but it works just as effectively, if not quite so strikingly, in the North Sea. And what you can see here is if we zoom in on this area here, we can really see the channel delineation coming out incredibly clearly. We can see the different channel systems, the way they're integrated. If you compare that with a conventional amplitude map, you simply don't have the same information. And if you don't have the information, you don't have the understanding. So by using this kind of visualization techniques, we can improve our understanding of what's going on and therefore improve our decisions. But as I mentioned earlier, it's not just about attributes, it's not just about having pretty pictures. We've got to be able to extract these objects out and create the 3D geological features that build up our models ultimately. So we need to convert these images into 3D geobodies. And that is very difficult when you've got a variable character in your system or where you've got a very subtle expression. So we can see here we've got 2 features, one north-south and one cross-cutting here. And they've got very different characteristics. And to detect these out using threshold-based techniques wouldn't really work at all. So we've developed the adaptive geobodies, which are a tool which will allow you to do a data-driven but interpreter-guided extraction of your feature. So if we could play the movie, Gary, hopefully we'll see a geobody to start growing. Here we go. So the geobody is now growing along this lower channel here, and we can see it extracting that out. And we'll grow another one up the top channel up here. And you can see that even though the character of the data is changing, we're still growing the geobody. It still tracks on that. We're going to now take out this cross-cutting one, but we've given it some pointers to help guide it because it's a subtle expression, so we've given it a path to follow, which helps control it. But the key difference about this is that we can now go in and manually manipulate that geobody. We can say, actually, I want you over here a bit more. I think you come down here. We could move it side to side if we like as well. And we can reposition it. Once we've repositioned it, we just tell it to adapt to the best fit of the data again. And you can see we've got different colors here. So the colors represent how well that geobody is fitting the data. So it's allowing us to override the data. It's allowing us to move the geobody and manipulate it. But then it comes back and says, okay, you put me there, but I'm not too confident about being there really, but I'll be there. So it gives you that feedback. It tells you where it's happy, where there's a strong boundary, and where there's more uncertainty. So you can focus your interpretation on the areas of greater uncertainty. So the adaptive geobodies are fantastic for channels, but they're also good in other situations, such as karst systems, salt, or even simply for tracking horizons. And now you can extract any feature that you can see in the attribute data. So far I've been talking about the geological expression workflow, starting from the seismic data, because that is where we've got the lateral information. But we mustn't forget about our wells, because ultimately our wells give us the ground truth. They tell us what's really down there. So we need to be able to integrate the well information back into the geological expression workflow. And we can do that by integrating interactive seismic classification with the well data. So using the wells to guide how you choose the number of classes and which different zones are different classes, but using the seismic data to help identify those zones away from the well. So we can incorporate that. So this is being developed in collaboration with Statoil, and I should also say that the adaptive geobodies was developed in an R&D project with Lundin Petroleum. But using well data and incorporating well data into the geological expression workflow highlights the huge difference in vertical resolution between your well data and your seismic data. Well data is much higher resolution than seismic data. So we need to make sure that the attributes that we do, any kind of analysis that we do on the seismic data, doesn't deteriorate the resolution that you have. And that can be seen with frequency decomposition. Frequency decomposition and RGB blending is a fantastic tool, but standard techniques have fairly poor vertical resolution just because of the filter sizes that are needed to measure low frequencies. So developing new techniques that actually give you high definition, in this case frequency decomposition, but basically high definition analysis of the seismic data is one of the areas that we're focusing on going forward to make sure that we can get the maximum information that we can from the seismic data without degrading the resolution. And you can see here quite clearly the improvements in vertical resolution that you have between the standard techniques and the new high definition techniques that are now available. So finally, to conclude, I'd just like to say that geological expression is the future of seismic interpretation because it combines an interactive, data-driven approach with an interpreter-guided aspect as well. It merges the data and the interpreter together for the first time in a truly integrated manner. And that leads to large productivity gains and also more accurate interpretations. So geological expression workflows now give us the power to make the most informed seismically driven decisions. And this leads to a more efficient path from seismic acquisition to ultimately our drilling, and therefore delivers more accurate results with greater certainty. So finally, thank you very much.
Thank you, Gaynor. Any questions about that? And if not, yeah, please, go ahead. Yeah,
okay. How does the business model work? Do you just sell the software, or you come with the software? How's that?
We do both. We sell the software. We also provide services. So we'll take your data and run these workflows on it in-house according to whatever objectives you have. But we also do on-site consultancy as well. So we'll also go into your office, help you with it, show you how to use it, and work with you on-site too. But ultimately, we are a software company, and our aim is to sell the software. But as I say, we do support that through services and consultancy as well.
It helps to know the fundamental model, presumably. In other words, if you want to have a channel system that you want to interpret, or
yes, yeah.
In a way, it's like saying that the kind of algorithms need to know what they're working towards.
That's right, yes. So it helps to have an objective, but that objective can be quite wide, from sort of data reconnaissance. just general structural imaging or amplitude anomalies. So it can be quite a wide-ranging objective, or it can be very, very detailed. So is this fault one fault, or is it a fault splay? Is it multiple faults? So it is very scalable in that sense.
Ian?
Yeah, Ian Jack again, and sorry about that. Just as we have annual conventions, so does the computer games and graphics industry have their annual convention. They had it 10 days ago in San Francisco. Did your company have people there looking at it? And if not, should you have had?
No, we didn't have people there. It probably would be good, yes, to have people there. We do, our software development team, I think still have quite strong links to other aspects of the computer industry. We have software developers who have come from the games industry, and we've also got software developers who've come from the medical imaging industry as well. So I think they've still got links to those industries, but we don't present there, or we don't kind of actively participate, if you like, in the games industry.
Okay, that's Jerry Lunn. You're doing some of the processing on the graphics unit, and one of the trends, it flip-flops a bit between having data local to the workstation versus having data on a large storage system. Obviously, when you're going into the GPU thing, and with some familiarity with ffA stuff, it helps significantly to have the data on the workstation. So how are you attempting to address that, given that at the moment the move is towards having data in admittedly local, but still behind the wall in a data center, and therefore you do have issues with getting data from the servers to the processing unit?
Yep, absolutely. That's having the data local in our sort of current software. Having the data local is key to enable that rapid access to it. The way we're looking at this, we're looking at different forms of sort of local caching and local blocking to be able to pull data in from remote sources and to control it, or to temporarily store it locally so that we can access it to the graphics cards, so that when you're doing the graphics processing or any interactive kind of analysis, what you've got is temporarily stored local, and if you're likely to need more of that, it's going to be transferring it across in the background. So the aim is to be able to be fully supporting of remote storage systems. But tied in with that is the idea of minimizing the data overload. So getting rid of the need for intermediate volumes. So by having interactive workflows where you can see options, which are done just maybe on one slice or a series of slices which you can pan through, but seeing options and then choosing what you want, so that you've made that decision before the bulk of the processing is actually done, to take away the need for test volumes or intermediate stages coming through. But yeah, that transfer is something that we're looking at as well.
Okay, and I had a question. I mean, when I go around Tullow Oil, we've got a couple of floors of interpreters all sitting using Petrel on twin screen Dell workstations. And what you're talking about isn't some visualization gizmo that sits on top of that. I mean, your business vision is you displace all that.
Yep. So our software has its own integral visualization system. We started off originally just as a plug-in to other people's visualization systems, but it very soon became apparent that what we wanted to do, the other visualization systems couldn't do. Things like the RGB blending. So when we first introduced RGB blending 6 years ago, nobody else could do that. No other visualization system could cope with that kind of display. So we had to make sure that our application could do that and could blend that. And so our application is standalone, but it does have links with Petrel. It's got links with GeoProbe, it's got links with OpenSpirit as well, so that you can transfer things directly through. Having said that, most other systems, Petrel is the exception, still can't display RGB blends.
Okay.
Certainly not at 24-bit resolution. Yeah.
Okay. So in a couple couple of years' time, I look forward to Tullow Oil having a couple of hundred of your systems. And
We will happily sell
Nothing.
Tullow Oil, a couple of hundred of
and nothing from Schlumberger at all, which would be just great. Okay, thank you for that, Gaynor.
Thank you.
Okay, now I need to do three things.